In today's lecture, we'll discuss AVL trees and we'll discuss the C++ implementation of several functions in the AVL tree. So let's start with the discussion. First of all, we'll see just the prototype of the AVL class. So first of all, we have this AVL node, that's a structure, and then we have type def, or you can say redefine this the pointer of this AVL node as position and AVL tree. We'll use these two type defs in other functions. So like you see, this position function, this position redefinition is used here in the retrieve function, and it's also used in another function that we'll see in the next slide. Then we have this AVL tree. You can see that we have redefined it to be a subtree, right? So we'll use this pointer whenever we want to point to a subtree in the AVL tree. So this redefinition or type def is used in almost all the functions in this class. So you can see that it's available in almost all the functions. In this lecture, we'll discuss the insert function, and we'll see the C++ code of this insert function as well. Whereas for the delete function, we'll just see the idea, and there are parts of codes that this delete function uses that are very similar to this insert function. So at the end of this lecture, I'll ask you to implement this delete function on your own. So let's start. The first definition, that was the structure of AVL node. Let's see what this definition is. So the definition is that in this AVL node is very similar to a normal binary tree node. It has an element, it has a left pointer, it has a right pointer. This element type is definitely it can be any type, any user defined type as well. That is why we can say that this is a template based implementation. So after these three elements, we also have this height element in this AVL node. We could have just called a routine that calculates the height of each node, but that would be computationally expensive. That is why we have inserted this height parameter in each node. And whenever we want to check the height of a node, we just read this parameter. And when we insert this node, we'll set this parameter as you know that in an AVL node, we discussed that in an AVL node or an AVL tree, it's the first condition is that it should be a BST. So for a BST, we know that whenever we insert a new value, for example s, it is compared with the value in a node. For example, if this is the root node, the x will be compared with the y, and if the value is smaller, then it goes in the left branch, otherwise it goes in the right branch. And the whenever this node is inserted, it is inserted at a point that is null on the corresponding side of the parent. So a new node is always inserted as a leaf node. Hence we can say that the height of every node upon insertion should be 0. Okay, so we'll, of course, whenever we add a child to a node, we'll modify this height of the parent as well. So this height is what we keep modifying upon every insert and delete. So let's see. The first thing where we use this height is a free function height. So this free function height, this is not part of the class. It's a free function, and it receives a position, that is the pointer. I said, as I said in the previous slide, that we'll use this position, which is the AVL node pointer in this function height. So this is a free function. It receives a pointer, and why this function is defined as a free function is that we discussed that in an AVL tree, the height of a null node, this double dash is a null node, is -1. So we cannot read the height of a null node because the memory is not allocated. That is why we used a free function and passed a pointer into this function. Whenever the pointer is null, the function returns -1. Otherwise, it reads the height inside the node and returns the corresponding height of the node. So this function will be used specifically for this. In fact, this function is defined specifically for the null pointers. Otherwise, we could have just read the height member from the node structure. So we have this height function. We'll use this function in the insert function as well as in the delete function. So let's see how we use it. So let's move on to the insert function and see how the insertion is made in the AVL tree. So this is the insert function, and you can see the return type is an AVL tree, which means that this function should return a pointer to an AVL node. And then it receives a value x that needs to be inserted into the tree. And the second parameter is a pointer. And as I said, this pointer we should read it as a subtree, part of an AVL tree. Initially, this would be root for the first one. Then this function recursively moves down and keeps checking this value x with the value at the root of that subtree. And if the value is smaller, it goes to the left. And if the value is bigger, then it would go to the right of the node. So for the first call, when we have the root of the entire tree as a parameter here as t, this would be t, and we check this value x. For example, the value of x is 5 and the value of y is 10. X is smaller than 10, it would go in the left branch of the root node. And what we would do it is that, for example, if I take this example and call the insert function on the root node, the t, that is the root node, it's not null. I would not go in this if, and I would go in the else part. And I'll see that this value x is smaller than the value of the root node. X is 5 and the value in the root node is 10. So x is smaller than 10, which means 5 is smaller than 10, which means that I would go into this if, and I would call this insert function recursively. This is the same insert function, and this is a recursive call here. And I have called this function with this t left, which means that left of the root node as the parameter. So now I would insert this x in this subtree. Okay, I hope that this subtree definition of this subtree makes sense now. So I call this function insert again and pass this value 5 and the left of the root node in the insert function. So let's see how it's done. Moving back to the first if condition, I have reached here, and now this pointer is, for example, null. So if this pointer is null, the first if condition would be true, that t is null and the value 5 is to be inserted here at this pointer, null pointer. So what I do here in this first if is that I create a new memory. This is the new memory. Then I assign the value x in the element part, and then I set the left and right pointer to be null, because a newly inserted node would always be the leaf node. That was what we saw in the BS3 as well. So I have created a node that is a leaf node, but I have not connected this node with the parent. So let's see how it's done. This if is complete here. I would not go in the else part, in which I have another if. So I would not go into this entire part, and I would not go the else of this if as well. So I would not go in the third if as well. And when this else is completed, this is the part that is the end of this insert function. So what it's doing is that it's setting the height of the newly created node. So the newly created node that is 5, the value, it has the value 5. I set the height is equal to, that's the formula to calculate the height of a node, that I would actually compare the height of its left and right subtrees. Whichever is the bigger number, I would add 1 to that height. So if a node has this left branch bigger than the right branch, then I would, if the height of the left branch is h of l, the height of this parent would be h of l plus 1. So this is what I've done here, is that I have added 1 to the maximum height of left or right subtree, and then assigned it to the node of to the height of the parent. And now this t is returned. Remember, this insert function, it had a return type of AVL tree, a subtree. So this t, which means that the newly created node, the address of that node is returned. And as we saw in the example, that we moved from root node to the left of it, which was null, and we created a new node for that point, but we have not adjusted the pointer. Let's go to the backtracking of the recursive call. So let me draw this tree here as well. I had 10 in the root, and I have created a new node 5, setting its left and right pointer to be null. And this new node was created on the basis of this recursive call. Now on the backtracking part of the recursive call, remember a recursive call has two phases. First phase is the forward pass. On the forward pass, I've created a node, and now on the backward pass, I'm going back and assigning this address to the parent. So this is the part where this call to the left child of node 10 was made. So this call returned the address of this node 5. So the address of node 5 is assigned to this left of the node 10. So this pointer now points to node number 5. So this is done on the basis of this assignment. Okay, now this 5 is added to the node 10, to the left of node 10, in an AVL tree after the BST insert. This was simply a BST insert, but this time we have used the recursive definition instead of using the iterative definition of the BST implementation. If you want to see that definition, you can go back to the lecture video that I already shared for the BST implementation. But this implementation is the recursive one. So for the AVL implementation, after this BST insert, I need to check the balance of the tree as well. So in this, if I am checking the imbalance, and then if there is an imbalance, I am adjusting the tree to keep it an AVL tree or to maintain the balance height property. So in order to check the imbalance, what I would do is that I would check if this node has created imbalance in its ancestors or not. Let's say that, for example, this was the last call of the insert, and I had a parent of this 10 as well. For example, the parent was the value 15. So I had a node that was the parent of this node 10. So in that case, after adding this 5 as the child of 10, I'm here on the node 10. Okay, in this call. Now I am checking the imbalance on the node 10. So how I would check the imbalance is that I would check that the height of left of node number 10 and the height of right of node number 10. So the height of left is 0. We set that value to be 0, remember? And the height of right, this function height, whenever we pass a null pointer to it returns -1. So the height of right is -1. So -1, and the left was 0. 0 minus -1. Remember, I used this left as a first parameter of this subtraction, because I just added a node towards the left of node number 10. So if any side is bigger than the other one, it should be the left one. Okay, that is why I have written this left before this right. So the height of left, that should be possibly bigger than the height of right, and that's true in this case. 0 minus -1, that would be 0 minus -1, that would be 1. So if this difference is equal to 2, then the imbalance is there. But in this case, the difference is not 2. It means that I would not go into this if, and I would simply go to the end of the insert function. And remember, at the end of the insert function, we had 2 lines of code where I adjust the height of this node t. In this call, on the backtracking, now t is the node number 10. So at the end of this insert function, I am adjusting the height of the node, of the current node, that is node number 10. So the height of node number 10 is equal to maximum of height of left was 0, that was the height of node 5, and the right was null. So for the null pointer, the height is -1. So maximum of these two is 0. 0 plus 1 is 1. So the height of this node number 10 becomes 1. Okay, and I return this node number 10 from this function as well. So further backtracking in the insert function, I have returned from this to the parent, and I have set the height of this node to be 1. Okay, so the height of new node was 0, height of its parent is 1, and I backtrack to the grandparent. Let's say that the grandparents also has a null node on its right, just to create the imbalance, just to show you the imbalance here. So if this 15 had a null pointer on its right side, we again came back to this call specifically. Um, and let me just erase a few points from this part, so I can write or fill the parameters again. Okay, so now I have reached on this node 15, and the t is now 15, and I come back from this call. I assign the address returned from this insert was the address of node number 10, and it's reassigned to the left of the node 15, which is of course redundant, but to generalize the function, we can reassign it again to the left of node number 15. So now we are on the node number 15, and we need to check its parents. So the height of left of this 15 node, that is the node number 10, is 1. Okay, so the height of left is 1, and the height of right is of course a null node, so it is -1. So it would be 1 minus -1, which is equal to 2. So at this time the condition is true, that the node t, that is 15, it is an imbalanced node, because the difference between the height of left and the right subtrees has become equal to 0. So in order to adjust or shuffle the tree or rotate the tree, we use this code. And in this code, you see that we just check if the insertion was made towards the left of the child or towards the right of the child. So if the insertion is made towards the left of this node, then this case is the single rotation case. Otherwise, if the insertion is made towards the right of the left child, then this is a double rotation case. So in this, if I'm checking if this x, the new value that was inserted, it is smaller than the left of the left of the 15, that is it is compared with the 10, with the value 10. So if this value is smaller than 10, then it is added towards its left and a single rotation is required. But if this x is bigger than the left child, that is if 5 were bigger than 10, then we would have made a double rotation with the child. But in this case, x is smaller, so this if is true, and we perform a single rotation. We'll see this code, single rotate with left, in a later slide. But if a single rotation is made correctly, then what it would do is that we had 15 here, 10 on its left child, and 5 towards further left. So after the rotation with the left child, what we would have is that 10 would become the parent, 15 would go to the right of 10, and 5 would still be on the left of 10. So that would be the final tree. Okay, and this single rotate function performs this rotation, and it returns the address of the new root of this subpart or subtree. So the new root is node number 10. So this address is required. Okay, here. So after single rotation, instead of having 15 as the root of the tree, remember this t is the root of the subtree that needs to be rotated. And after the rotation, I return a new root, and that is assigned to the value to the variable t, which means that now after this single rotation, the root is now node number 10, and I would not go in this else, and I would go to the last two lines of the insert function here and set the height of this node number 10 as well. So this is now node number 10, and the height of node number 10 is again adjusted after the rotation. So in this case, the height would be the height of left is 0, right is 0, 0, and 0 plus 1 is 0. Initially, it's 0 plus 0 plus 1. Okay, sorry, in fact, 0 plus 1 is 1. Okay, so 0 plus 1 in this case, because 0 is there on both sides of the tree. So maximum is 0 plus 1 is assigned to the height of number 10. That was already 10, that was already 1, but still we reset the height because sometimes after the rotation, the height of the new root node would be different than the one that was already there. And then we return this t again from this insert function, which means that after this rotation, this 10 should be connected to the upper part of the tree as well, which means a recursive call on the backtracking. It performs some insertions and it may also perform some rotations on the tree. In that case, it needs to connect the new root node to the upper part of the tree. So it returns the address of the new root here. Okay, so which also means that when we call this function for the first time, we call it like this: root is equal to insert in the root the value 5. So after this insertion, if the root node is changed, then this is assigned to the root of the tree as well. So this is important part here. Whenever you call an insert function on this AVL tree, you make the call like this, that the return of this insert would be the new root, and it should be assigned to the root of the tree, which also says that this insert function, it is a recursive function. Of course, it has two parameters, but this function should be called from another insert, for example, data function. That is the public function, and it only receives the value. And this public function should call this private function. This insert should be a private function and should not be called by the main function or the user directly. So user calls this function insert data with the value, and then leaves the rest to the implementation. And in the implementation, what we do is that we use this 5 as the value as the second parameter and pass this root as the first parameter. And we call this function like this, that if it performs a rotation and a new root is discovered, then the new root is assigned to the root of the tree. And maybe after this call, the function only returns true. Maybe it only return true to indicate that this insert data is successful. So that's another part of the story. Uh, so this was one case when I have inserted towards the left of a left child. Let's see another example where I insert towards the uh, right of the tree, and we'll see how that works. So for example, if the value that we want to insert in a tree that has a root as 10, I want to insert 15 in this tree. In that case, the first call would be for the node 10. The node is not null. I go into the else part. The value is bigger, so I would not go in this if. We already saw this if. We go into this third if. So the value 15 is bigger than the value 10. So I call this insert function on the right side of the node 10. So I call this recursively and move this value 15 in the call. Okay, so going back now, this next call that is performed on this child, this right child of 10. Here this child is null, so I create a new node, assign the value 15 to this node, make its left and right child to be null, assign its height, that is these last two lines, assign its height to be 0 and return the address of this node to this call. Okay, so after this call, I receive the address and I fix this to the right of node number 10. Now this is the tree, and after adding node towards the right of this child, this is the mirror image code or mirror code of this first if or the second if. And in this, I have replaced the right with the left and left with the right. So I have interchanged the parameter. So the height is compared as I've added towards the right. So I put this height of right before the height of left, and subtracted this left height from the right, and check if the new insertion has imbalanced the node or not. And if an imbalance is made, I check if the newly inserted value, it is added towards the right of the right child or towards the left of the right child. Okay, so if it is added towards the right of the right child, then this is a single rotation case, and if it's added otherwise, it's added on the left of the right child, and that makes it the double rotation case. We'll see these rotation codes soon after this slide, but this is of course the mirror of the single rotate with left, and this second call is of course the mirror image is the image of double rotate with left. So let's see how these rotations are made, and if they also, those functions also maintain the balance property of the AVL tree or not. So let's go to that detail. Okay, so this is the rotation function. Let's redraw the previous example. We had this 10 on the root node, then we had this 5 on, we added 5 on the left of this node. In fact, this 10 was not the root node. It had a 15 as a parent as well, and this was 15 was the root node, and this 15 had its right child as null. 10 also had right child as null, and we just added this 5 on the node, and after backtracking we have reached this node 15 as the T node, and we saw that this 15 was imbalanced, and we call this single rotate with left on this specific on this node. Um, let's or we can just okay, let's go to the, or let me use another example. Instead of uh, making a single rotate with the left child, let's do the single rotate with the right child, because that rotation I already showed you. Let's take the case of let's say this is the case that we just added a new node 15. The height of this node is 0, the height of this node is 1, and we just checked on the rollback phase of the recursive call that this 5 is now imbalanced. It has a left child as null, 10 has the left child as null. So now I've detected the imbalance, and I've detected that the insertion of this 15 is made to the right of the right child. Okay, so a single rotate towards left is required on this node number 5, or what you can say is the single rotate with the right child. Okay, so this 5 is here passed as k1. Okay, now let's see how the rotation is performed. We declared a pointer k2. Remember, this position is the pointer to the node, so k2 is the pointer to the node, and I assign the address of the right of k1 to k2, which means that this node number 10 is now k2. Okay, so node number 10 is k2, 5 is k1, and now I have stored the address of this node number 10 in the pointer k2, so mm, I can change this pointer. I can actually change the values or the address stored in this right pointer of node number 5, because I have stored the value in the variable k2, the address in k2. So what I do here is that I just change the um, in the single rotation. I know that what I have to do is that this right child, if there were a child, it would go towards the left of this branch, so it would become the right child of 5. Remember, the single rotation is that if there is a left child of this child node, this left child rotates and it attaches itself to the node to the parent of this child. So this I assign this on this line. What I do is that I assign the address of k2's left to the right of k1, which means that this is null at this in this example. And what this specific line does is that it assigns the same address that is assigned to the left of 10 to the right of 5. So this right of 5 becomes null. Earlier I had the address of node number 10 to the right of 5. So now I have these two parts. First part is that this 5 has a right pointer as null that I just changed, and this 10 It has right child as 15, and the address of 10 is stored in K2, address of 5 is stored in K1. So I have broken down this tree into two parts. Now in the next line, what I do is that I assign the address of this node number 5. This is K1 has the address of 5. This to the left of K2, which means that uh, this is node number 10. It has this right child 15, and I assign the address of K1, that is 5, to the left of node number 10. So this is the connections that I make after these two calls. So first connection is that I move the child of 10, the left child of 10, to the right of 5, and then I assign the node number 5 to the left of node number 10. So this is the rotation. Now the remaining part is that this 5, before this insertion in of the 15 node, the height of this node was 1. Remember? So it still has the height 1. 10 after the insertion of 15 has the height 1. 15 has the height 0. I need to adjust the height of these two nodes because they are actually rotated, and the height of 10, it has moved upward. It might change, and 5 has gone downwards, and the child that was actually calculating its height is no more here on the right of this 5 node. So the height of 5 is definitely going to change here. So let's see. First I change the height of 5 because this is now the new child of 10. So I change the height of this node first, and then I go to check the height of node number 10, because after adjusting the height of node number 5, it may change the height of node number 10. So I need to adjust the height of child first. So I adjust this height of K1 first, and use the same formula to check the height of left child and the height of right child are compared, and the maximum is big, and I add 1 to actually find the height of the parent. So the left and right of the node 5 are -1, the heights are -1. So -1 is the maximum. I add 1 to it, and the height becomes 0. So this 1 is updated, and now the new height of node number 5 is 0. Right? So for the next statement, I adjust the height of this node number 10, and you see the height of node number 5 is changed now. So I check the height of right and left children. So here I have directly used the K1 height, that is the left of 10. So the height of right and height of left, they are compared, and the maximum is big, that is 0 again. 0 plus 1 is 1. So the height of K2 is not changed, it's again set to 1. And now the parent of this subtree is node number 10. So I return this K2, which is the new root node of this sub part of the tree. So after this rotation, the tree is now that 10 is on the root, 15 is towards the right of this node, and 5 is towards the left of this node. Height of 5 is 0, height of 15 is 0, and height of 10 is 1. And now this 10 is the new root node. This rotation function returns the address of this 10, and you saw in the insert function that after the single rotate with the right child, a new root node is returned and assigned here on the place of t. In this example, the t was 5, but after the rotation, this t should be updated, and the new root is 10, and the address of 10 should be stored here. Okay, so that is what I've done here. Return the address, and this t is further moved up the tree to connect to its parent. So this is what this insert function along with this rotate function do. So that's the single rotate with the right child. Let's see an example here. Here is the tree, and I inserted this node 60 in this tree, and upon backtracking, I found that the node number 20 is imbalanced. I call this K1 and call the function single rotate with left. This K1 is node number 20, K2 becomes the node number 40, and then what happens is that on this line, um, on this line, I set the right of K1 to be the left of K2. So this 30, it is connected. This was the node number 20, and I set the right of this node. Okay, the right of this node to be left of K2. Left of K2 is 30. So on the right is 30 now. Okay, so 30 moves from here to this side, and we already had a 10 here on the left of the 20. So this is the K1 part, whereas the K2 part is still there, and I need to adjust this K1 inside K2. So this should be like this. So on the next line, what you do is that we assign the address of this K1, that is node number 20, to the left of K2. So K2 is 40. So this is node number 40. I assign this K1 towards the left of this node. Okay, and the remaining right part of the node number 40 remains same. This is 50 here, and this is 60 here. So this is how the rotation is performed. So just the simulation that 40 becomes the new root node, 20 comes to the left of it, and 30 goes to the right of 20. This 30 was the child of node, left child of node number 40. It goes to the right of node number 20. So this is the resulting tree after a single left rotation. Okay, now the single rotate with left child, the mirror image of that function. You see now where I had right, now I use left in that place. So wherever I had left in the single rotate with right function, uh, I replaced that right with the value left for this left function, and where I had the uh, uh, left, I interchanged it with the right. So left and right keywords. These two keywords are interchanged, and the new definition is single rotate with left child. We discussed this with examples in the previous lecture. You can go to the playlist and see those that lecture if you are not aware with the or not comfortable with the idea of rotation. So this is the code for single rotate with left. Now let's move on to the double rotation code. So double rotation, if we just recap it, if we have this tree here, we see that the higher side or the heavier side of this K3 is the left side, and this the further heavier side is the right of K1. So this becomes the inside case, and to adjust this imbalance, what we do is that we pull some weight from the inside of the tree towards the outside side of the tree. So first rotation is performed on the K1. When the rotation is performed, K2 takes the place of K1. K1 goes further down towards left. So the first step is that K3 is here, K2 comes here after first rotation, and K1 goes further down on the left of K2. B is on the right. B moves to the right of K1. A stays here on the left of K1, and we have this C node on the right of K2. Then we perform another rotation on K3. And after rotation on K3, K2 becomes the root node, K3 goes to the right of it. So this is the final shape. Okay, that was the concept. If you're still not comfortable with it, you can go back and see the rotations lecture in the playlist. Okay, but for the code, the idea that we just picked up from this example is that first we perform a single rotation on K1. So we need to reuse the single rotation code here, and this single rotation is with the right child. Okay, and then the single rotation on K3 is with the left child. So this is the code that we receive this K3 as the node that is imbalanced, and what we do is that first we call the single rotate with right on the left child of K3, which is K1. So first this rotation is performed on node K1. After the rotation, we attach this K2. This K2 is returned as a new root node of this subtree, and this K2 is attached to the left of K3. Okay, so this particular shape is what we get after this call. Okay, K2 is attached to the left of K3. Then what we do is that we call another single rotation on this K3, and this time the rotation is with the left child. Okay, so the tree is rotated on the right, and the new root, that is K2, it is returned from this double rotation code. Okay, so it's also important that we return the address of this new root node to the parent of this subtree. Okay, so this is the code of double rotation with left child. Similarly, we can have the double rotation with the right child as well. So for the double rotation, we just change the calls for the right. We interchange the left and right in the function calls. Okay, so that is the double rotation code. Okay, so here is the worked example of a double rotation, but we have already done that. Let's go to the deletion part of the AVL tree. So the deletion of the AVL tree, as I said at the start of the lecture, that we'll just discuss the idea with few examples to show all the scenarios of the deletion, and then the code is very similar to the insert function, and we would like to reuse the code, the blocks of codes from the insert function. Okay, so I would like you guys to write that code, but before that, let me explain the idea of the deletion in an AVL tree. So the overall concept is that what we want to do is that after the deletion, if we have an AVL tree, after the deletion, a BS tree, an AVL tree is a BS tree, so it should remain a BS tree and it should be height balanced. Okay, so which means that if we have an ability and we delete something from that tree, what we want to have is that if we have a BST, we still keep it as a BST and we satisfy the height constraint as well. So let's see if a delete operation um, disturbs the height property or balance of an ability or not. So in this tree, if we just delete this node number 9, we have this tree, and we see this is a BST definitely, but now if we see this 7 is, it does not have a right child, which means that this is an imbalanced imbalanced BST. Okay, so this is not an AVLT, which means that deletion in an AVLT, it affects the balance of the tree. So we see another example. It not only breaks the balance of the tree. You see, this was the imbalance. What other thing that is deleted is the balance factors. Initially, we had some balance factors here. We had this balance factor as 0. There was no difference in the left and right subtree. Um, this had the balance factor of 1. This 4 had the balance factor of 1. 7 had the balance factor of, before the deletion, it had the balance factor of 1. Okay, so after the deletion, if we just adjust this tree, what we have is that we do not have this balance correctly mentioned here. Okay, so from this tree we deleted 3 and we reached to this tree, but this time the balance factors are not correct. We need to adjust those balances as well. So upon every deletion, there are two things. The first thing is that we saw in the previous slide that we could have an imbalance. The second thing is, if we just delete a node, we might not have any balance, but still we need to adjust the heights or the balance factors of the ancestors of this deleted node. So these are the two things that we need to make sure that we adjust after every deletion. Okay, so uh, so the overall idea is that we adjust the balance factor, and the goal is that first we perform a BST delete in the tree. And after the BST delete, what we do that is that we maintain the balance of, or we perform some rotations and adjust the heights of the resultant tree. Okay, so this is what we do. Let's just review the step number 1, that is the BST delete. So the BST delete was very simple. Uh, it had 3 scenarios. The first scenario was that if you want to delete a node that has no children. For example, if we delete this node number 62 from this tree, this deletion as a BST deletion would only need me to move to just change this right child of 50 to be null. I do not need any other change in this tree if I just perform a BST delete. Okay, so a node having 2 children a node having no child can be deleted, or a leaf node can be deleted by just setting the appropriate or corresponding uh, pointer of the parent to be null. Okay, that was the first case. So we can delete the 62 and set the right of 50 to be null. But for an AVL tree, if we just note that as well, This blue area, this blue part is the part that actually this is the these are the ancestors for which the AVL properties might have been affected. Okay, but let's just put it on a hold and see the other scenarios of the deletion. So another scenario is that we want to delete a child that has only one. We want to delete a node that has only one child. So, for example, if we delete this node 84 from this tree, for a BST delete, what we just require is that we set the left child of 88 to be node number 80. We just change the address of the address stored in the left child of 88. Okay, so that would be that we just move 80 to the left of 88 and release the memory of node number 84. Okay, so that's the deletion. But once we perform the deletion, this blue area is again the action part of the AVL tree where the where the AVL properties might have been affected. Okay, let's move on to the third case. When we want to delete a node with two children, a node that has two children. So let's delete this node number 78. If you want to delete this node number 78, in the binary search tree lecture, what we saw that we can do is that we move this entire left subtree of this 78 to the right of this tree. And when we move this subtree that is rooted at 50 towards the left, this 78 becomes the node which has only one child, that is 88. We can adjust this 50 to the left of 80, but we know that this deletion would actually increase the height of this right side of 44. It would be actually affect it very the height would be affected, and it might become the double of the height that was previously there. So what we do is that we use another idea that we just go to the right of this node, and then we go to the extreme left of this branch. From 88, we go to the extreme left of this branch and find a node that is the extreme left, and it has a null pointer on its left side. Now, this is the node that is the smallest node in this entire subtree. Okay, so we pick the smallest node from here, we delete it from here, and we move this node in the place of 78. If we do an in-order traversal of this tree, this subtree for example, rooted at 78, we see that the sorted data would be after 78 we have 80 in this tree, and then we have 82, 84, and so on, which means that this 80 is the next value of 78 in the tree. So what we actually achieve from going right and then going extreme left of the tree is that we pick the immediate next value of 78 and replace that value in place of 78, which means that 80 is the smallest value in this subtree. It can be on the root of the subtree where all the bigger values are towards the right and the smaller values are towards the left. So this is the technique that we use in this deletion. We go to the right of the deleted of the node to be deleted, and then go to the extreme left and pick this node number 80. What we do is that we replace this 80 in place of 78 and perform a deletion on this point. 80 is deleted from this point, and when we deleted 80, 82 became the left child of 84. Okay, so this is the adjustment that we do when we delete a node with one child. Okay, so now if the deletion is performed in this position, all these ancestors, they are the ones whose balance factors might have and height might have been affected. So in an AVL deletion, we need to look at these nodes to adjust the balance factors and the heights of the tree. Okay, so that's the recap of the BST delete. Now let's go to the of the BST delete. Now we'll go to the step 2 of the deletion in the AVL tree. The first part is I'll just recap that. Now we'll see how we can adjust the heights of the tree. So in this tree, for example, if we perform a BST delete on this node number 32, what we have is that previously the node was this tree was a balanced tree. But after deleting a node on the shorter branch, this 32 is already on the shorter branch. You see, this branch is the longer branch. If we delete 32 from this branch, this branch becomes further shorter. So in that case, um, what we need to do is that after deleting 32, we need to check the balance factors of 17 and 44. Okay, so the 17 is the first position that has the issue, and these are the ancestors whose balance might have been affected. So um, what we do is we can just perform some rotations on the if an imbalance is found on node number 17 or node number 44. We can just perform some the rotations, and we can adjust the heights. Let's see how we do that. um, in the delete operation, of course, the rotations are actually the reverse of the rotations in the insert function. If we have performed a deletion on the left side of the tree, then we perform a rotation further towards the left, which means we move the weight on the right side of the tree to the left. Okay, just to adjust the missing weight of the deleted node. We move nodes from the other side. We move weight from the other side to the side where the deletion is performed. So we start checking the imbalance. The 17 is not imbalanced, so we move further back, which means the recursive call moves up in the actually reverse part of it, um, rollback part of it. So we reach this node number 44. To check the balance, we use the snippet of the code from the insert function, that the height of the left subtree and the height of the right subtree. Deletion is performed in the left side, so we subtract the height of right from the height of left side. Okay, so what we do is that we compare the height of right child, which is 78, minus the height of the left child, that is 17. So in that case, the height of 78, in this case specifically, the height is 2, and here the height is 0. So it would be 2 minus 0 is equal to 0. That is the part that we picked from the insert function to check the imbalance. So this 44 is the imbalance node. Now, what we'll check is, again, now we'll move into the exact code of the insert function, that we have found that this part is heavier. So we'll check if the heavier side of 78, the child of the imbalance node, is the left side or the right side. If the left side is heavier, then this is the inside case, and we perform double rotation. First rotation is performed on 78, and second rotation is performed on the 44. So first rotation on 78 is towards right to move this heavier side on the outside of the tree. Then the second rotation would be performed on 44 to pull this heavier weight to the left of 44. Okay, so that would be the entire idea, but let's see it uh, in the animation on the slide. So we find that this 44 is imbalanced, and then we find that the imbalanced side is the inside side of 78. And then what we do is that we start performing the deletion, the rotation part. We call the imbalanced node as A, the child as B, and the heavier side, the root of the heavier side as C, and we perform. You can see this is the in the double rotation code. This was the K3, and this was the K1 side, and this was the K2 side. So first we perform the rotation on K1, and then we perform the rotation on the K3. If you just remember the code of the double rotation. So after this, these specific rotations, what we would have is that we move this 50 on the place of 78, then we move this 50 upward as a root node. So this is the final tree after the rotation. 44 goes to the left, this left child of 50, 48, this goes to the right of 44, and this 78 is the right of 59. Okay, so this is the final tree after the double rotation, but the scenarios to check which rotation is required are now the reverse of the insert function. We deleted a node from the left subtree, but we performed a rotation which moved the heavier side from the right to the left, to the side where the deletion is made. So this is how we did it, and these are the conditions that we call the imbalanced node as node number A. We call the first child, the heavier child of node number A as B, and we call the heavier child of node number B as C. So then we perform the rotation, or as I said, that we can also call them K3, K1, and K2 respectively. And then we perform the rotations. Okay, so the idea is complete. So let's see one more. The last point in this overall discussion is that after performing one rotation, I would just should we just stop the backtracking process and not check the imbalance of the ancestors further up in the tree, or we should keep checking the imbalance? So let's see how we do that. Maybe some of you might have got the idea, but let's see. For example, we have this tree, and what we do is that this is the shorter part of the tree. Okay, so what we do is that, for example, if we perform a deletion in this part of the tree, for example, if we just delete this AT from this tree, so the part of the deletion that we have just seen is that we would find that this parent is imbalanced. So we would perform a single right rotation on this node, and what we would get is that this 60 becomes the root, and after the rotation, this part of the tree is now balanced. This specific part of the tree, this subtree, is now balanced. But as you saw, or you can see here, that this deletion has actually decreased the height of this subtree. Initially, the height was, for this point, the height was actually 2. Okay, but after the deletion and the rotation, the height is now 1. So this subtree has decreased in height, and this has definitely affected the balance factor of its parent as well. So after a rotation, a subtree becomes shorter in height, and a subtree that is now shorter in height, it might affect the parent as well. So this scenario, the height is decreased, and this 50 is imbalanced. So we keep performing the rotations until we get to the root of the tree. So that is how we perform the deletion, that all the ancestors of the deleted node, we need to check their balance. In fact, after a rotation on one node, we still need to keep checking the imbalance further up in the tree, and we can stop at the root. So this 50 is imbalance, and we can rotate it towards the right to adjust the balance of the entire tree. So this is it. That's it. Now what I would like you guys to do is that this is the homework for you guys. You need to write the C++ code for AVL delete function that we just discussed. Then, in fact, this finding minimum, finding maximum of the tree, this is the code that you should have written when we discussed the BST, because this is the similar in AVL and BST. The only difference is that the nodes or the tree is now balanced. Okay, so these two functions, you should write them. In fact, we saw a slight glimpse, a small glimpse of these functions in the deletion function as well. So that's the hint for you guys. Then what you need to do is that we for this implementation, we had this height member as height as the member of the struct AVL node. But what I want you guys to do is that you need to write the code to find the height of a node if the height is not known. You can say that we have a binary tree. We do not know the height of any node. So if you want to ensure that this node is an AVL tree, you need to first find the height of every node, and then you can check the balance factors. Okay, so in that case, you would need to find the heights of the nodes by recursively going down in the branch and find the longest branch. That is what you need to do recursively, or maybe you can do it iteratively as well. But you need to write the code to find the height of a node, given that the height of that we do not know, we do not know the height of any node. We do not have the data number height in the node, in any node. Okay, so then the reverse of the height is the depth, which means that you need to start from the root and move to that specific node and find the number of steps that you've taken to reach this node starting from the root node. So that is the reverse of the height function. You need to write that function in C++ as well. Then a generalized function that if a given tree is a BST, you need to check if it's an AVL or not, which means that you need to find the height of every node, and then you need to check if the Bayes vector is maintained on every node or not. Okay, so the given tree is BST. The smaller values are on the left side of every node, and bigger values are on the right of every node. But the balance factors are not calculated. So you need to calculate the balance factor of every node. And if the balance factor is maintained for every node, you would return true. Otherwise, you would return false. Similarly, if a simple binary tree is given, now you need to check two properties. You need to check the BST property as well as the balance property. So this is a more generalized function that you might need to call on a data set to check if the tree is if the data set is in the balanced condition or not. And you can, if you find that that a data set that is already stored in an array is an AVL tree, is in the form of an AVL tree, you can efficiently search, or you can efficiently perform some required operations on the tree. But you need to have the guarantee that this is an AVL tree. So this function is a very useful function that I want you guys to implement for practice, and you need to do it in C++. I hope this implementation is clear. If you have any questions, you can ask in the lecture during the lecture hour, and we'll answer those queries during the next lecture. Okay, thank you.